Hello everyone, what I want to do now is talk about the matrix of a bounded linear operator and talk about, very briefly, about self-adjoint operators. I'll have one more video on unitary operators and some examples and connect them to self-adjoint and normal operators. I'll define normal operators and I'll do examples, and then we'll just dive into chapter 3. Okay, so so let's say A is a bounded operator, and let's say it's a bounded operator on some separable Hilbert space. Okay, so so let's say X is in my separable Hilbert space. A is bounded. So what we can do is, for any orthonormal basis EI, any countable orthonormal basis EI, H is separable, so there is an countable orthonormal basis. We can write AX as this sum here. AX EI EI. So the convergence here is in the Hilbert space norm. All right, well, what we could do is play this game one more time, but with AX here. Make this inner product a little bigger. So I'm not going to write H here. So this is going to be AX. Do this again. Let's use J here. So J equals 1 to infinity. Sorry. So I'll use continuity in a moment. So it's A times this sum here, J equals 1 to infinity. X, I want to write X in terms of this orthonormal basis EJ, not write AX. I mean, you could do that. Won't really get you all that much if you do that. Okay. Right, so all right, so so let me use continuity of A. Okay. So yeah, of course, as I said a second ago, this here is what X is, X EJ, this sum. So use continuity. We get AX is going to be the following. So it's going to be J equals 1 to infinity, X EJ, A EJ, EI, EI. Okay, right, so kind of going back to linear algebra, we often call this xj, and this here is a ij. Okay, so in some sense, we have written out A as a matrix with respect to this orthonormal basis EI. Okay. And so we say in this case, in the basis, orthonormal basis EI, the ith component of AX, which is nothing more than the coefficient of AX with respect to your orthonormal basis vector EI. So this whole thing here that I'm circling is going to be what I denote AXI. Well, this is just given by this formula here. Just like, oops, that. So it's AIJ XJ. Exactly what I have here, AIJ XJ. Okay, right, so we say that AIJ is the matrix of A with respect to the orthonormal basis EI. Okay. So as the book indicates, and this is in the book on page 30 something, second. Page 33. So as the book indicates, this is not, sometimes this is not very useful. And in particular, the main problem in studying operators via its matrix is that it's very hard to relate the norm of A and the matrix AIJ. It's just in general extremely hard. And there's really no good, there's really not much of a good relationship between the norm of A and properties of AIJ. In particular, there's certainly no, A is bounded if and only if AIJ satisfies whatever. That's just, nothing like that is really known. On the other hand, one very useful kind of result is the following, and this is called the Schur test. It's really called the discrete Schur test, because it's really a statement about bounded operators on little L2, if you think about it. I'll make as a homework the continuous Schur test for integral operators. It's in some sense virtually the same proof, but anyway, right, so and this is a surprisingly useful result, certainly in, for example, Kehei's book, or really most of his books, he uses the Schur test quite a few times. I'll do an example of how it's used. Okay, so what we have here is, well, let me just state the theorem. Let's assume there exists pi positive, gamma beta positive, where the following is true. Okay. So what we want is a criteria for a bounded matrix given its, we want a criteria for a bounded operator, or for an operator to be bounded given its matrix with respect to some orthonormal basis. And an easy test is the following. So if this is true, or both of these are true rather, this sum here is less than or equal to beta pj. And this sum here is less than or equal to gamma pi. Oops. Then we can say that A, the norm of A, is less than or equal to the square root of beta gamma. I should say probably most often, in fact, when you use the Schur test, not always, but probably most often, you just set the p's to be 1. That's often what you do. So in particular, when p's are equal to 1, well, you have this condition here. So yeah, as long as basically, the sup overall j here and the sup overall I here is less than or equal to respectively beta and gamma, then you have a bounded operator. Yeah, sometimes you do want this in its full generality. Okay, so there is a bit of ambiguity of what I'm even defining A as. So let's be a little more careful. So here A takes H to H. Is defined by the following, and this is really a definition. It's the sum here that I basically said before, that you can always write a bounded operator as basically right here, Aij x inner product ej Aij x ej ei. Okay, right. So just a note. Well, here you can check, just plug in any fixed ei and ej. You can check, yeah, very easily that. Make sure I get this right here. Yeah, Aej ei, according to this definition here, is actually Eij. Okay. Right. So yeah, so we're actually being a little more general than just saying if we have an operator whose matrix is satisfies this here, then this is true. Here we're saying, in fact, if we just have complex numbers Aij where this is true, then this defines, this is defined as, so this operator defined, Ax defined by this sum here, is bounded, and yeah, in this case, Aij is actually the matrix of A with respect to this orthonormal basis Ei. Okay, so the proof is as follows. And the proof is actually just literally a clever Cauchy-Schwarz inequality twice. It's a really, really nice proof. So what I want to do is I want to prove, first of all, I want to prove that this actually is even in my Hilbert space. And we know that I can do that by showing that this here is in little L2. So that's my task. And so what I want to do is get, in particular, an estimate for the following. I'm going to estimate this sum right here. absolute value of aij modulus aij modulus x ej. Well, this whole sum here squared. Okay. Right. So if I can, ultimately what I want to do is get that this is less than or equal to so yeah, I want to get that this is less than or equal to gamma beta times the norm of x squared. And if I can do this, then I'm done because, well, so over here a bit. Well, in particular, if I can do this, then AX is an element in my Hilbert space, and by just using, well, we know what the norm of AX is. It's just going to be norm of AX squared is going to be the L2 norm squared of this sum here. So we'll get here, because this is true for any x, that the norm of A is less than or equal to gamma beta. If we can do this. Okay, right, so this is what we need to prove. All right, so let me add and subtract, or sorry, let me multiply and divide by something convenient. Okay, so, right, so I'm going to put the xej first. I'm going to divide by pj to the 1/2, so I have to multiply it. I'm going to do that in a moment. So as I mentioned, I'm going to use a clever Cauchy-Schwarz inequality, actually two of them. So I'm writing modulus aij as modulus aij to the 1/2 modulus aij to the 1/2, and I want the pj's to cancel. So it's pj to the 1/2, pj to the 1/2. So my first Cauchy-Schwarz inequality is going to be with respect to this here and this here. Sorry, I need a squared here. If I don't have this squared here, that completely screws things up. So just by the little L2 Cauchy-Schwarz inequality, this is going to be less than or equal to j equals 1 to infinity, x inner product ej squared over pj. Well, square gets rid of the 1/2. Aij modulus times this sum here, aij, well, square gets rid of the 1/2, pj. And that's good because I know the sum here, aij, pj, and I should, sorry, if it wasn't clear, both of these are, well, this is for all I, and this is for all j. Okay. Sorry, have that switched around. This is for all j, and this is for all I. Okay, so yeah, in particular for any I, this is less than or equal to pi. So by our assumption, this is less than or equal to the following. Yeah, and as I mentioned, I'll state this for boundedness criteria for integral operators. And you're going to do almost the same thing, just use Cauchy-Schwarz inequality for integrals. Yeah, and I'll leave that for homework. Yeah, so our assumption here is that this whole thing here in the brackets is less than or equal to pi. It's gamma pi. Right, so pull out a gamma here. Okay, so I want to do, first I want to, well, okay, so sorry, we only need Cauchy-Schwarz once. I'm going to interchange the sums now, and there's no problem in doing that. There's absolutely no issue whatsoever because everything is non-negative. Okay, I'm allowed to do that certainly. Just basically Fubini's theorem, which holds for non-negative sums certainly. All right, so what I want to do is I'm going to pull out this term here. It just depends on j. So if I do j first, it's x ej squared in a product over pj. Okay. So we've pulled yellow. We've pulled this out, but I'm still left with this right here in the I sum. But we're going to just use the other condition. So pj. But this sum here for each j is less than or equal to beta. Beta times pi. This is pi. That. It didn't magically become a j, it's pi. Right, so this is less than or equal to, by the other assumption, well, just this whole thing is less than or equal to p beta pj. And, well, that basically completes the proof. Because the pj's cancel. And all we're left with here is, well, the norm of x squared. So we've accomplished our task, which is to prove that the norm of ax squared, well, it's well defined. It's an element in my Hilbert space by proving this is an L2. And in particular, the L2 norm squared of this blue here is less than or equal to gamma beta modulus x squared. Yeah, and that implies a less than or equal to the square root of gamma beta. All right, so let me do an example. So actually, before I do that, just one more definition. So we say A is diagonal. We might have a homework on diagonal orthogonal projections in the book. So we say an operator A is diagonal with respect to the orthonormal basis EI. If, well, the matrix itself with respect to this orthonormal basis is diagonal. I should say in a lot of different research areas, operator theory, signal processing, there's a very applied math, there's a very important, or many different possible notions of almost diagonal operators, A, in the sense that Ij is really small when I is not equal to J. We won't really talk about that, but there's a lot of different notions you can find. So it's a pretty rich concept, diagonal operators and kind of almost diagonal operators. But all right, so let me do an example, which is actually a pretty important example. Different areas of analysis or even signal processing. And this is this example is discrete convolution. I mean, it's, you know, in theory, important in data science when you do convolution neural networks. Yeah, in practice, when you do neural networks, most people don't really care about theory because it works really well. So why care about theory? But anyway. All right, so let's say C is given by, and actually in the next video, I'll connect discrete convolution to Fourier series. I'm going to define a convolution operator, and we can actually figure out the operator norm using Fourier series, which is really neat. I'll tie into unitary operators and unitary equivalence. So let's say we have a L1 sequence. H is just little L2 of the integers. Let's say this is just the standard orthonormal basis. So that. Now I should clarify what I mean by that, because in some sense the natural orthonormal basis is Fourier series. All I mean here is that EI equals a lot of dots here. Well, you get the point. Just a whole bunch of zeros, except everything is zero except we have one in the ith spot. You can check. This is an orthonormal basis. Okay, let's say Aij is Ci minus J. So by definition, AXI is going to be, so here I'm actually writing this as an element in little L2, which is really the same thing as just writing out the component, the ith component of AX with respect to the standard orthonormal basis for little L2. So this is going to be the sum here, Ci minus J xj. Okay. Yeah, so very reminiscent of convolution that we've seen, in last semester, and you've probably seen elsewhere with respect to an L1 function. Okay. So yeah, this is an example here using sure test where we're going to set all the PIs to be 1. All right, so in this case, yeah, so this sum here Well, because I is fixed here, both of these are going to be equal, and they're just the L1 norm of C. I should say C is, yeah, well, I said that, sorry about that. Okay, and so, right, this is Aij right here. So remember, when the PIs are equal to 1, our task is to just basically just literally prove this here, which we've done with beta and gamma equal to just the L1 norm of C. All right, and so this implies that this is a bounded operator, and this is less than or equal to the L1 norm of C. So, yeah, and of course you can basically do, you know, a kind of like a Young's inequality, discrete Young's inequality type argument, or just a clever Cauchy-Schwarz inequality itself to prove this. But it's just much quicker just to use the Schur test. So it's a nice example of the Schur test. And actually, we're going to show in the next video, well, I won't say, well, if you've seen unitarily equivalence before, we're going to show that A is unitarily equivalent to an operator associated to Fourier series, and we're able to figure out what the norm of A is. All right, so what I want to do now is talk a little bit about self-adjoint operators. I'm going to prove a result that is later in the book. So let's say A is bounded on some Hilbert space where A star equals A. If this is true, then we say A is self-adjoint. A lot of times we'll say it's Hermitian, in particular when we're dealing with a complex Hilbert space. Right, so we have the following easy proposition, which you probably proved in linear algebra. I'll leave this as an easy homework. Don't know if I'll collect it or not, but just so much I can collect. So if A is Hermitian, then should be THEN. And AXX is an R for any X in H. And I should mention that the converse is true if we're dealing with a Hilbert space over the complex numbers. If AXX is real for any X in H, then A is Hermitian. The converse is false if we're dealing with the Hilbert space over the real numbers. So for example, take probably one of the easiest examples you could really think of, which is H as R2 as a vector space over the reals. And there's a million examples here. Certainly all inner products are real, so there's nothing really to worry about that. So just take anything that's not self-adjoint, like 0, 1, minus 1, 1. So we know that as an operator on R2, the adjoint is just 0, minus 1, 1, 0, just a transpose. As I mentioned, obviously all inner products are real. For any x in R2, this is real. Sorry about that. And yet A star is not equal to A. So A is not self-adjoint. Okay, what I want to do is finish this video off by proving a rather remarkable feature about self-adjoint operators. So first of all, if we have H in my Hilbert space, then we can write the norm of H in the following way. Well, it's just the supremum of H inner product Y over all Y with norm 1. Well, by Cauchy-Schwarz, this is less than or equal to the norm of H, norm of Y. And, well, if Y has norm 1, then this just equals the norm of H. On the other hand, so let me put this here. Well, the norm of H, assuming the norm of H is not equal to 0, you can fairly trivially write this as H, H over norm of H, and that's less than or equal to this supremum here. So, right, so we have equality. Norm of H is sandwiched between the supremum and the supremum. Or rather, yeah, anyway. So we have equality. Okay, so, and of course, we have also equality when H equals 0. Everything is just equal to 0. Okay, so what does this mean? Let's say A is a bounded operator on this Hilbert space. So we can write the operator norm as follows, by definition, and setting H to be AX, we can write this as an iterated supremum as follows, AX, Y inner product. And you can write this in the following way. You can check, really like a 511 exercise. It's just a supremum over all these inner products over all possible values of X and Y. Equals 1. Okay, and this is certainly bigger or equal to the following. Well, just setting X equal to Y, this is bigger or equal to the supremum of all these inner products over X with norm 1. And let's say this is, let's call this big M. So really, on the surface, it should look like the supremum here is much bigger than m, because in the supremum, we're looking at all different x and y with norm 1. And in general, it is much bigger. But if A is self-adjoint, and bounded, then in fact we have equality. Right, so let's prove this to finish off the video. So the proof is elementary, but it's very clever. And this is on, I should say, page 88 of the book. They use this as a lemma to the proof of the spectral theorem for self-adjoint compact operators. I'll definitely get to that later. I actually want to prove the spectral theorem for compact normal operators. But I think it's worthwhile to go over, really earlier, because it is a pretty important result. So it's obviously enough to show that the norm of A is less than or equal to m. We already showed trivially that the norm of A is bigger or equal to m. So we have two observations. Essentially, the book, so I'm going to follow the book's proof, and the book's observation B on page 88 is just what I have here, basically. So, yeah, I'm going to do things, I'm going to maybe do the order of things a little differently because it's not very intuitive in the book. And I should say the proof is a very clever elementary argument that you often do in operator theory. You often do proofs like this in operator theory. So if this tickles your fancy, no, there's no lack of operator theory researchers in our department. Professor Kwan, Professor Yang, Professor Stessen, Professor Zhu. Not really sure I would consider myself operator theory. But anyway, so sorry, it's enough to show that this is true. So two observations. The first one is that for any h with norm, any h not equal to 0, we can write AHH modulus as follows. Well, we're essentially multiplying and dividing by the norm of h squared. Of course, m is a supremum of AXX over all x with norm 1. So in particular, this is less than or equal to m, h squared. And of course, this is true when h is 0, because everything is 0. And B, what the book calls C, is the following, which is really the crux of the proof. For any f and g, A f plus g inner product f plus g minus, this here, A f minus g, f minus g is equal to 4 times the real part of AF g. And here you're going to use the self-adjoint property. You're going to, if you want to check this, I would check it. If you have any doubt, really just expand f plus g out and f minus g out here, and use the self-adjoint property to get a lot of things canceling. And if we have a real Hilbert space over the reals, there's no real part, of course. Okay, so right, so let me use this with a clever choice of f and g. In particular, let's say we have a V with norm 1, where let's assume AV is not equal to 0. If it is, well, what are we doing? We're looking at the norm of A, so we're looking at AV for V with norm 1. So we can assume that this is not 0. So let's set X to be V plus AV over norm of AV. Like that. Okay, so what we're going to do is set F to be V and G to be AV over the norm of AV. So I want to look at F minus G, which is just V, and I'm going to set that to be Y. V minus AV over the norm of AV. Right. So by B, AXX minus AYY. Well, yeah, so this is going to be A F plus G, F plus G, A F minus G. So we said that this is going to be equal to 4 times the real part of A F, which is just V, inner product with G, which is AV over the norm of AV. Which is, of course, just 4 times the norm of AV. So what does this mean? This means that the norm of AV is equal to AXX minus AYY with this judiciously, picked X and Y. Well, certainly this is equal, well, yeah, so this is a real number, obviously. I mean, we know this by just this equality here, and we know that because A is self-adjoint. So we can take that norm of AV is equal to this, which is less than or equal to its absolute value, and then use triangle inequality. So it's AXX plus AYY. Okay, so let's use A twice. Right, so this is going to be less than or equal to M norm of X squared, M norm of Y squared. And this, well, let's use the parallelogram law. Well, this is equal to pull out the M here. And if you remember the parallelogram law, this is so this is for parallelogram, PAR, by the parallelogram law, is X minus Y squared plus X plus Y squared in norm. Well, what is X minus Y? X minus Y, well, that's just going to be, the V's cancel, so it's 2 AV over the norm of AV. All right, and what is x plus y? Well, x plus y is just, where did it go? Sorry, right here. Well, that's just obviously 2v, because the AV over norm of AVs cancel out. So this is definitely a clever proof. I would not be able to just pull this, just off the top of my head, think of this proof. And a lot of operator theory, as I mentioned, is clever like this. Not very, a lot of it is not necessarily deep, but very clever. Well, this has norm. This is parallelogram law says that this is 1/2 times this. So it's an m over 2. So this is going to be equal to, well, this is just norm 1, so it's 4. So it's 2 squared. This is also 4. So this is just going to be 8 over 2 is 4. So what have we proved? We have proved that the norm of AV is less than or equal to 4m. For any v with norm 1. So that, of course, implies, sorry, there's a 4 here. Let's go back and double check. Sorry, this is 4AV. Makes more sense. Sorry about that. Forgot the 4 here. Right, it's 4 times the norm of AV, less than or equal to 4m. So that means the norm of A is less than or equal to m, and that finishes the proof. Right. As I mentioned, there's going to be one more video on the basics of operator theory, and then we will just dive into chapter 3. All right, so long. Take care. Bye-bye.